Okay, so what I'd like to talk about today is this idea that there's certainly many jurisdictions have some fairly ambitious renewable energy goals. California is probably, at least until very recently, was the most ambitious. Hawaii has now surpassed us, but
right.
Okay, so there's essentially California's goal is, and these are typically implemented via what are called renewable portfolio standards, which effectively mean that a geographic region has to procure a certain fraction of its energy from what are called qualified renewable resources. These are resources that the agency, the state agency, designates as qualifying to provide this renewable energy. And California has currently a 33% renewable portfolio standard by 2020. It has recently extended it to 50% by 2030. One of the big issues with respect to this is the fact that the incentives that these sorts of programs create, in particular, the usual way that you actually finance one of these facilities is through what's called a power purchase agreement. As well as, and so what this can do is effectively give the owner of the unit an incentive to locate, if you like, where they earn the highest revenues, largely because of the fact that construction costs for these units, for the most part, although there certainly are differences across locations, are pretty similar on a dollar per watt basis. And so what happens is that if what you're trying to do is maximize the return from your investment, you're typically going to maximize the revenues that you earn. And what this does is at least it seems to me, it can create at least what in the language of economics would be called an externality. And an externality, what I'm going to call a reliability externality, in the sense that because I want to locate my unit where I think I'm going to get the highest revenue, that may not cause me to locate my unit where I enhance the reliability of the grid to the greatest extent possible. Meaning that what I'll do is I don't really care when the power comes or how much comes when it comes. I just care that I earn the greatest amount of revenues from this renewable resource unit over the course, say, of the year. And so what this can mean is that we're going to need to have more dispatchable backup units on the system, so to provide operating reserves, to provide ramp up and ramp down when the units disappear, if to the extent that that occurs at in a very volatile fashion, the output that these units provide. And moreover, it may imply spending more money on storage because of the fact that in order to manage that intermittency, I probably may need to invest more in storage. And so the question that I was interested in is this idea of, well, how actually potentially big could this reliability externality be? Meaning that this fact that because people are maximizing revenues rather than system reliability in making their locational decisions, how much more volatile is the output from the renewable resources that exist in California? And this just is a set of table just to show you that the ISO is planning for precisely this sort of outcome as well. This table gives you sort of a listing by season of the year, by effectively year of deployment in terms of how much things like regulation reserves, this is automatic generation control in the upward direction, or regulation down, automatic generation control in the down direction. This is dedicated generation capacity that's going to be used to keep the system in balance in real time. And you can see for each of the years as you go out into the future, those numbers are getting much bigger. And to the extent that we can get people to invest in renewable, the intermittent renewables in such a way that we limit the volatility in output, we can perhaps limit the amount of these sorts of operating reserves that we need to hold, and thereby reduce the cost of integrating a given quantity of renewable energy into the grid, or achieving a given renewable portfolio standard goal. Okay, so what I want to talk about today is really, as I said, to try to characterize at least this reliability consequences of different portfolios of wind and solar locations or generation capacity in California. And so what I'm going to do is borrow a little bit from finance and come up with essentially an efficient frontier. For those of you who are familiar from finance, an efficient frontier in the sense of output, expected output of renewable energy versus risk of output of renewable energy, or to use the more precise term, the standard deviation of the aggregate output of renewable energy. We'll come up with frontiers, meaning that values of the portfolio weights for the various solar and wind investments that essentially minimize the output variance subject to achieving a given level of output. And then the other thing, just to show that this sort of reliability externality story is likely to be operating, we're also going to compute an efficient frontier in terms of hourly total revenue to renewable energy locations frontier. So meaning that we'll compute the expected hourly revenue and the standard deviation of hourly revenue frontier for the same set of wind and solar locations. Now, one of the things that's important to know about California is that we run what's called a locational marginal pricing market, which means that prices get set at up to 3,000 locations every hour of the day. And so what this means is, I'll show you in a few minutes, is that you can have quite different price patterns at different locations in the grid. And what we'll do is we're gonna compare the mean standard deviation value to the actual capacity shares to those on that efficient frontier, and to sort of see how far away are we from that efficient frontier, both in terms of output space and in terms of total revenue space. All right, so just to give a little preview of what we find is that we find that we're pretty far away from the efficient frontier in this output space. And what it says, based on the numbers that we compute, is that we literally could increase the hourly output of renewable units by simply rejiggering the locations that we installed the capacity and increase that expected hourly output by about 48, as it says on the 48%, with no real increase in risk of the hourly output. For hourly revenues, we are a little bit closer to the efficient frontier, meaning that we can increase aggregate revenues for the system, not for the system, for all renewable resources by about 26%, yet without increasing the variance in that hourly revenue. And in that sense, that's precisely consistent with the logic that I spoke of right at the beginning of the talk, of saying we're a lot closer to the efficient frontier in revenue space than we are in output space, largely because what we think that new entrants are doing is they're entering where they think they can earn the greatest revenue, not where they think that they're going to yield the highest annual output. Since what you're interested in as an investor is to maximize your return, and that return is price times quantity. It's not just simply total output. Okay, so the other thing that we find in terms of the results, as you'll see in a sec, is that the capacity shares, the shares, if you like, of investments that we get from the efficient frontier, for the most part, what they do is they say there are many locations that we would have been probably better off not investing any capacity in if what we're trying to do is stay along that output efficient frontier. We'll talk a bit more why that's likely to be the case. One of the reasons certainly is the fact that the investments that we actually did over time in California, they didn't take place all at once. They took place over, say, at least the last 15 years. And so what this means is that, that part of it is just simply reflecting the fact that, that when these investments were made in time. The other result that I think is interesting is the fact that one of the explanations, and we'll give an explanation for why we think that some of the investments at certain locations in the grid would not have occurred if what we were doing is investing according to the mean variance frontier, can be explained in terms of, once again, sort of borrowing some results from finance theory as well. All right, so this is just showing you a map of California with all of the locations that we set prices. So what happens potentially, particularly when there's lots of wind or solar output or a very hot day or a day with a little bit of wind or a lot of wind, is that you can get very different prices at different locations. This was today a rather mild day. So, for the most part, the fact that all the dots are colored the same color just simply says there's not a lot of transmission congestion, meaning that the power can flow pretty much anywhere in California and not have to worry about bumping up against transmission constraints. All right, so this is sort of the, for those of you who like math, this we'll give it to you, but the basic idea here is all we're doing, the first part is just to say we're constructing a portfolio of units, which essentially says that you're computing this capacity weight, which is the capacity at location J divided by the total capacity. That is, and then what we do is multiply that thing by what's called the capacity factor at each location. The capacity factor at each location is just simply equal to the megawatts of capacity of the unit divided by its hourly output. Then what we do is we construct this portfolio of the units, which is just equal to has the nice convenient representation that you can see right here, that it just says, look, you just take the capacity share times the hourly capacity factor times the total capacity of renewable energy. That is equal to the hourly output, total output that you get from all renewable units in California. And then what we want to do is we can compute this for the actual capacity shares, but what we're going to do is compute the counterfactual capacity shares, which essentially minimize the variance of the hourly output subject to achieving a given level of hourly output. And we're going to trace out the set of points that do that by essentially solving an optimization problem for each different value of the expected output. Then the other part of the thing that we're going to do is we're going to use data from the California ISO on the hourly output of all wind and solar units at all locations in the state. And that's going to give us the mean of the hourly capacity factors at each location, and then it's going to give us a big giant variance covariance matrix, which just tells how each of those capacity factors are correlated, meaning that when the capacity factor, the rate at which you use the capacity at that location or is producing electricity, when that thing's very large, the value at some other location is very large, and that's going to tell us where we get the benefits from diversification. So the only thing that, just to talk about here, is we're going to work in terms of just weighted average capacity factor and standard deviation of the weighted average capacity factor, because the aggregate output is just a scale up times the total amount of capacity they have in the system. And so what we'll do is just compute the efficient frontier in terms of that. Now in terms of revenue, the story gets a little bit more interesting because of the fact that, as you can see, the total revenue decomposes into, there's a component that's not only the expected price at that location, the expected capacity factor at that location, there's also this fact that the covariance between the price at your location and the capacity factor at your location. So for example, thinking in terms of, say, like a solar unit, that covariance matrix could potentially be positive in the sense that prices are higher during days when the capacity factor for solar is high, assuming there isn't too much solar at that location, because if there's too much solar, that could push the price down. And then the variance, I'm not really going to try to give you intuition for that thing, but just to say that it can get quite complicated. But we do exactly the same thing, and we compute the hourly total revenue for the portfolio of all renewable units, which is just computed in the same way. And then what we're going to do is compute that efficient frontier based on data from that. So what we have is the data as we have hourly prices from the real-time market in California. We have those hourly capacity factors. We have all the data that we need to be able to compute this sample mean of this vector of hourly revenues per unit of capacity and the variance covariance matrix of that as well to then get some idea of what the efficient frontier looks like. Okay, so as I said, what we have is data for 1 calendar year in California for all of the units, and there are, at the time in the sample period, there's 40 wind locations in California, 13 utility scale solar locations, and as we said, roughly 3,000 megawatts of wind, about 500 megawatts of solar, so fairly small, but California is scaling up, and so what we're going to do is essentially compute those portfolios that the portfolio, if we can compute for any arbitrary portfolio what its mean aggregate output is and what the variance or standard deviation of that is, or the mean revenues on an hourly basis and the standard deviation of those revenues on an hourly basis from the data that we have. So I think it's helpful to just start out with a sort of some idea of what's the ideal that we'd like to be shooting for. The sort of way that we'd ideally like to think about it is that we've got this covariance between, say, the output and the revenue at location I and location J. We've got the variance at location J. We can think of this thing called the correlation, which is just the covariance divided by the square root of the two variances. And what we'll do right at the start is just to show you that the ideal situation would be that we'd like it that the renewable output at every single location is independent of the renewable output at any other location, which means that those correlations are all zero, because to the extent that those correlations are all zero, the more locations that we have, the variance in the aggregate is going to reduce just simply because of the fact that, according to the same logic that Las Vegas makes money, would be the same logic that the variance in the renewable output would decline, in the sense that because these are independent events, pretty soon, with almost certainty, you're going to get a certain amount of output each hour. Now, the problem is to the extent that there's a high degree of correlation, that goes away. And so what we come up with is, we'll just show you a simple index to say, this index that we come up with is essentially a 45-degree line in the graph of, so what it's saying is if this index scales linearly with the number of locations, then we think of it as this is something that is indicating independent identically distributed. The other one is that if the index goes up really, really fast, then effectively what that means is that the correlation is very, very high. And so just to show you, here is the case of, so what we have is the solid line here says for the portfolio of the 53 units that we talked about, this would be what this index would look like if all of them had the same capacity factor at each location and all of those capacity factors were independent. However, the line right here, the black line right here, is in fact that same index for the actual capacity factors at all 53 locations. And so what you can see is that it heads up really nonlinearly and really fast. And what that's saying is that there's a lot of contemporaneous correlation between the locations. And for those of you who understand linear algebra, all I'm graphing is the cumulative sum of the eigenvalues of the positive definite matrix there. So if that made any sense to you, then you're in great shape. But if not, the simple way to think about this is just to say, the closer that this guy is to the corner up here, the more correlated all of them are. So if you go to the next one, you say, okay, let's just do the solar locations. So the solar locations are the dotted line starting at 0, going up to the 13 solar locations that we talked about, okay? And what you can see here is the dotted line up there is virtually up in the corner, which means that the solar locations are extremely positively correlated. You can see for just the wind-only locations, it's not as bad. That's the dotted line there, and there's the 45-degree line. But again, for the wind locations, there's still quite a bit of correlation. And for revenue, it's even worse. What you can see is the corner gets, the guys get much farther up into the corner, which essentially says that the revenues you're getting are also very highly contemporaneous correlated. Well, what does that mean? Well, to translate that into English, what it's really saying is, if it's a sunny day in California, you get lots of solar output. And local weather patterns really don't seem to matter. That it's pretty much sunny days, and that's pretty much the only reason that you get solar output in California, solar output differences across hours of the day in California. Whereas with windy days, there appears to be some evidence that there are differences across locations in terms of, say, perhaps weather conditions and other kinds of things that could mean that they're not completely correlated. You could think of, well, it's also, again, I think makes sense to the extent that there are mountain ranges or other kinds of things that are going to separate these weather systems that are leading to differences in the wind output. The other thing that's interesting from this is to say that combining the wind and the solar doesn't really seem to give us much greater diversification benefits than what we get from just wind alone. And so, you know, what it's saying is that it's not this ideal world that we have renewable output at every location and they're largely independent. It's much more like you flip the coin, and when the coin comes up heads, it comes up heads at all locations in terms of it's a good solar day. Particularly for solar, it's a good solar day, or it's a good wind day. There is probably a little bit less of that. It's a good wind day everywhere. But what it's saying is that there's limited potential for diversification, or another way to say it is optimizing that portfolio is really going to have some benefits. And so that's what we're going to explore right now. So what we do is we go through and we're going to compute the efficient frontiers, and I'll just show them to you. So what we've done here is we said, okay, let's compute, in this case, what do we have? We're saying this, for the orange line here, is saying take the portfolio of solar locations and change, if you like, the weights that you put on the capacity factors of each of the solar locations and minimize the standard deviation of that hourly output subject to a given level of the expected hourly output or hourly capacity factor. And this is the envelope of those values. So in other words, the way to think about this is for any value on this, for any value on this axis here, what we're finding is the value that yields the smallest value for the standard deviation by choosing different values of the weights to put at each location, remembering that the weights all have to be positive because you can't build a negative generator. And then here, the green one says, suppose that all you're doing it is with wind units only. What is the set of feasible capacity factors and standard deviation of that capacity factor? And then the blue says if you take both the wind and the solar locations, how much better can you do? The first, I think, result that's interesting from this graph is just to show that, and then this square, the plus right here, that's the actual portfolio. All right, that is the value that we get for the average hourly capacity factor and the variance in the average hourly capacity factor or standard deviation of that average hourly capacity factor for the actual portfolio. The interesting thing, I think, is the fact first is that this is far from the frontier. The other is it's saying that certainly we wouldn't be doing very well if we only focused on solar. Right? Solar is clearly dominated, a solar-only portfolio is clearly dominated by a wind-only portfolio, and a wind-only portfolio is only slightly worse than a combination solar and wind portfolio. And then this circle here is just what's called the risk-adjusted maximum expected capacity factor, meaning that it is the value on this curve that has the highest ratio of this value divided by that value along all points on that frontier. So we can think of that sort of the, as I said, the risk-adjusted maximum expected capacity factor. So so the two big conclusions would be is we're not on the efficient frontier, we're far away. Now, as I said, it's not surprising that we aren't on the efficient frontier, given that investors have no incentive to be on that efficient frontier. But from the perspective of the operator of the grid, we'd certainly like that to be the case, because if what we could do is we could get the same capacity factor but reduce the uncertainty in the capacity factor, we could get by with less operating reserves and other kinds of things. And it would be the classical economist's free lunch, in the sense that we spent the same amount of money on capacity, yet we somehow got a less risky stream of output, which meant we don't have to have as much operating reserves. Or another way to think about it is, for the same level of uncertainty in that capacity factor, we could get a much higher level of it by just moving straight up to the efficient frontier. Okay. So this is just, not that you can, so what I've done here is I've said, let's compute efficient frontiers for each hour of the day. And so I realize it's kind of hard to see. I can't even see it myself, but it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, just go down. And what you can, and that's why if you look on these graphs, you don't see any yellow line, because you don't produce any solar energy in the middle of the night. But what you can see is that during the daylight hours of the day, this is where solar sort of earns its keep, as I'm sure you'd know without me even drawing the graph. But the interesting thing is that it comes out pretty steeply. So the big benefit is certainly in terms of diversification is in the middle of the day. Is just to sort of explore further. Why is it that you do want to include solar? Is largely because it does have this diversification during the peak hours of the day. All right. So we do the same thing now for the revenue efficient frontier, and we get a similar conclusion. It's just that you can see again that the degree of difference between the wind only and the wind plus solar frontier is smaller, but the other thing you see is essentially this guy is closer to the efficient frontier, consistent with the story that we told at the start that says, look, people are investing to maximize return. Maximize return means get the highest revenue that you can wherever you want to enter. But again, we can see that going with solar alone, at least on an average annual basis, would certainly not be the best way in terms of hitting your target. But still, again, you get similar graph to this if you decompose it, so that big revenues for solar tend to come in the middle of the day. No surprise there. Okay, so the next thing we were interested in looking at is to say, okay, what do points along the efficient frontier look like? In other words, are they investing, would someone who is along the efficient frontier be investing in the same locations that we actually invested at? So what the red squares denote is they show the share of total capacity in the state of California that is devoted to each location. And then what the various other dots show, so for example, the blue line, the green circles, and the green pluses, they all talk about points along the efficient frontier. And the interesting result is this is for the hourly output frontier. What you can see is that all the points on the efficient frontier tend to be concentrated very much in just a few of the locations. And a lot of these locations that have actual positive shares, all of these guys, the risk-adjusted maximum output, the minimum variance output, which is the one that essentially starts from the actual frontier and goes to the efficient frontier in the variance direction. So in other words, to go back to here, this guy is the minimum variance portfolio right here on the efficient frontier. It says stay at essentially the same capacity factor and move to minimize variance. This one is the maximum capacity factor. It says stay at the same variance or standard deviation and move up to the efficient frontier. You can see that in all cases, what it's showing is that you're going to effectively only put positive weights on essentially a few of the locations, and most of these locations shouldn't be on a portfolio that is on that efficient frontier. So one of the puzzles we're going to at least try to address is why is that happening? Okay, and hopefully give at least some answer. So the next thing we do is we say, all right, let's do the same thing for, let's see if that's true for the case of the revenues frontier. And again, we have the weights for the actual allocation. We have the weights graphed on the blue line for the risk-adjusted revenue max portfolio. And then we also have it for the other two portfolios that I showed you. And once again, you can see that for the most part, all of the weights are concentrated in a small number of portfolios, locations. And for most of the locations, there, at least it says there's nothing that should be invested, okay? So the final thing is just to say, well, do the locations that the efficient frontier for output identify, are those guys the same locations that the efficient frontier for revenues identify? And so what we've done here is we've graphed both the revenue maximum output portfolio weights and the output maximum risk-adjusted maximum output portfolio weights. And you can see that except for this guy right here, for the most part, there's quite a bit of agreement between the locations that maximize output. You can see positive weights here for the same guys that the blue line is positive. But again, there are scattered exceptions for things that maximize the output, which is, again, consistent with the argument that we talked about that says that, look, if you're investing with, to maximize revenues, you are going to choose different locations. And you can see that there are significant differences in the weights, which lead to that outcome. Okay, so why is it that we're getting these zero portfolio weights? Well, go back to the basic intuition from sort of finance theory. It says, what it says is that that what you want to do as an investor is you want to hold, you are compensated as an investor only for holding market-specific risk, not for undiversifiable risk, non-diversifiable risk. And so what we can do is we can construct these measures of what we'll call non-diversifiable output or revenue risk by just simply running a regression of the hourly capacity factor on the capacity factor at an hourly basis for the market portfolio. And what we pick for the market portfolio is this revenue maximizing share weighted average portfolio. And what we find is, for the most part, when we run that regression, both for the output and for the revenue, what we find is that most of the locations that get zero weights are locations with very, very large values of that beta coefficient. In other words, remember what the beta coefficient measures. It is equal to the covariance between that portfolio, the market portfolio right there, and the portfolio at that location. So what it's essentially saying is it's telling us that, look, when you get a little bit of wind output, that location really gets a lot of wind output, or equivalently, when there's very little wind output, that location has very, very low wind output, and as a consequence, you don't want to add it in to your portfolio because it has such a high level of market-specific risk. Okay, so what do these results mean? So the basic idea is, what we've got is, it certainly seems that from the results that we presented that the pattern of investment in some sense is not accounting for the reliability benefits that could be had from effectively recognizing that the location where I invest, it could potentially, even though it's making me money as the investor, I'm earning a high revenue. What it's doing is increasing the volatility of the renewable output in the aggregate, and therefore increasing the demand for operating reserves, increasing the demand for storage. How do we fix this sort of externality? Well, the first step would be is just simply start to recognize it and measure it. So the first step would be is to say, look, what we can do is effectively take data from the various ISOs, California ISO. We can compute these kinds of efficient frontiers. We can make this available, information available to potential investors, just so that people understand, that these renewable investors understand what locating their unit at each of these locations might do to the aggregate amount of output variability that we're going to get from the intermediate resources. The next step is we can incorporate this into the transmission planning process. So for example, it would certainly make a lot of sense to devote effort to expanding transmission into the regions that are effectively going to either increase the capacity factor in output without accompanying increasing the variability in the aggregate output of the system, and avoid investments in transmission into locations that essentially only increase the volatility without an accompanying benefit in terms of the hourly capacity, quantity weighted average capacity factor. The other is think about ways to, the typical way that we provide support to renewable capacity is essentially give strong incentives for the investor to locate at the location that earns the highest revenues. Going to different ways of providing support for these kinds of units could break that incentive to effectively just go to the location that earns me the highest revenues. There's a variety. The way that I suggest is transitioning much more to the same way that we compensate dispatchable units, is through essentially a fixed price, fixed quantity contract, rather than a fixed price full requirements contract that we typically give to most renewable units under the PPA agreements. And then the last area is something that I think is particularly interesting, is we could think of charging differential interconnection fees to say, look, we know that at this location, you're going to really impose a lot of risks on the system in terms of the fact of increasing the volatility. It's going to be more expensive for you to interconnect here, whereas other locations, we know that you're going to get much less risky pattern of output. We're going to make the interconnection charge at this location much less. And just to give you an idea of what this means, so what I've done in this graph is I've said, let's go to each location in the grid that there is an existing wind or solar unit, and let's increment by 1 megawatt, and let's see what happens to the percent change in the hourly output at that location, as well as what happens to the percent change in the variance in hourly aggregate output of renewable energy. And what we get is this kind of, in economist language, this elasticity. It sort of says, for a given percentage increase in the variability in, say, output, how much do we increase in percentage terms the expected output at that location? And what I've graphed here is the histogram of those values across all of the 53 locations. And what you can see is there's a considerable amount of heterogeneity. In case you can't see, it goes from -5 here all the way up to about 12 here. So what does minus mean? Minus means there are even locations in California at the moment where what you could do is you could both increase the average hourly output of renewable energy and at the same time reduce the variability. Okay, and in that sense, those are the locations you certainly want to hit first, because that's basically, you're getting two goods. You're reducing the amount of variability as well as increasing the average capacity factor that you're getting. And then other locations here, you certainly want to increase you want to get the highest increase in expected output for a given increase in volatility. Now, the other thing to see is we did this for the case of just the wind locations only. And and again, we did the same calculation. The only difference is you can see that now the variability, or the range of values, shrinks a little bit. And then if we go to the case of solar, you can see that the range of values shrinks even more. Okay, what does this mean? Essentially, what it's telling us is that, again, with the solar locations, it's going to be really hard. if what we're doing is everything with solar, we're going to just have an intermittency problem. Hopefully you can see that's off the charts. It's either a sunny day or it's not a sunny day. And we're going to have a lot of storage. We're going to have a lot of backup thermal generation. But to the extent that we take a portfolio of wind and solar, you can see that we really expand this heterogeneity. We really have opportunities to get significant reductions in the risk-adjusted output that we get. And so one of the things that we could think of doing is to say, okay, we could base our interconnection charges on the value of this thing, this measure at each location. So we could say, look, we'll pay you to invest at the negative locations because you are providing a net benefit to the grid, and we will charge you an interconnection charge that's essentially decreasing in the value of this index for positive values. So higher values of this, you get a smaller subsidy, lower values, higher values of that, you pay less, lower values, you pay more, as a way to essentially incent people to locate at places that is going to reduce the aggregate volatility in renewable energy. Okay, so just to finish up, the big issue I would just say is that this problem is only likely to get worse. California is unfortunately not following the prescription. It just recently added over 4,000 megawatts of new wind and solar, and mostly solar. So this volatility problem is likely to get much worse. The cost of balancing the system is likely to get much worse. We probably, hopefully, if what we would like to do is get renewables to essentially scale at a lower cost, we should probably think about these sorts of output diversification benefits and ways to try to capture those in the investment decisions that people are making in trying to meet California's renewable portfolio standard, or else we're likely to end up having to pay even higher for costs for the meeting the renewable portfolio standard. Okay, so I'll stop since I think I was supposed to stop.
Thanks, Frank. That was a very artful, if I could say, blending of theory and practice. And pretty sexy in its own right, but having done a little bit years ago of electric utility planning for California, the thing that makes it even sexier is the numbers. Revenue numbers are big, and as you pointed out at the end, getting bigger. And it's a repeated game. You play every day and every year. So it's a lot of cash on the line, if I could put it that way. Any questions, comments? Let's start with a couple of students in the back. Anybody? Okay, you got the quick draw. You get the quick draw award.
Thanks.
Sarah?
So within 2 years, well, by 2018, 2019, battery costs are going to be $100 to $120 a kilowatt hour, and that'll be widely available. And that'll also do with high power factor as well as high availability, high capacity. And so I would suggest you offset your higher charge to compensate to basically. Okay, so if I give you, if the project developer installs a bunch of battery power that reduces the volatility of the output of the farm, then they should not have to pay as much of your threshold of your charge as you're talking about. And you could actually, to make sure that you got good value for that, you could say, okay, well, based on whatever the lowest cost in the market is, that's the amount that will reduce will weigh that much, depending on how much you put in. And up to the point at which you don't have a volatility problem, where maybe you set some threshold, some sort of law of diminishing returns kind of a threshold, you can do that.
Yeah, no, I mean, I think it comes into here. I mean, if all you do is you make the renewable guys pay their imbalance charge, they'll install batteries. I mean, and right now, a lot of the imbalance charges are peanut buttered over the system, and that's certainly was something that was okay in the initial stages when we were trying to get renewables into the system, but to the extent that renewables are going to contribute a significant fraction, to the extent that you're buying, say, you're compensating the renewable resource owner with a fixed price, fixed quantity contract. He's got imbalances that he has to manage, and he's certainly going to want to invest in batteries or storage technology to the extent that that's a way to mitigate those imbalance charges. So, I mean, that's, I guess I would say, it's always important to remember that you have to create the business case for storage, and so the person that's going to make the investment in storage has to be compensated. Part of being compensated is they avoid these charges associated with balancing the system.
But could you do just to interject a little bit, could you do an analysis with your system to keep score about whether the battery investments are being made in the right locations?
Yeah, I mean, you could certainly, I mean, for the scale of renewables that are coming in the system, you're going to need some massive batteries. I mean, massive storage. I mean, it's...
so the market is big.
Yeah, yeah.
It probably is a market, but the market is big.
So, very nice mathematics. In engineering, we have the term inappropriate technology. I don't know if math has a similar term, but did you really intend to, from the beginning, show why renewables are false god in California? Because that's the way it is. I mean, everybody knows the longitude defines solar output, and everybody knows whether it's onshore or offshore wind defines the wind output in California. So I mean, your math is great, but this is something that we've known for ever.
Great. Yeah, no, I think it's great.
I mean, you must know that there was a unit, as you referred to it, last year that was asked by Cal ISO to not do a maintenance and to be ready at a moment's notice to supply air conditioning power if it was too warm in the Central Valley. It cannot be done to these guys. Right?
Yeah, I mean, I guess I'd say
what that unit was.
What you're saying may be well known to you, but I don't think it's the extent of the correlation and the extent to which these benefits exist. Right. That's all I'd say. I mean, I personally would say it certainly was news to the ISO, and they're quite interested in extending the study to more up-to-date information. But yeah, I mean, if you knew it, congratulations. But
that unit produces 8% of California's energy.
Which does?
That one unit.
Which unit? There's no solar unit that produces 8% of California's energy.
No,
there's no wind unit that produces 8% of California's energy.
That's right. It's Diablo Canyon.
That's nuclear.
And now Ohio has nuclear in the RPS. California doesn't because of politics. So there's the fundamental problem. That's why the inappropriate technology point comes up.
Yeah, I mean, I can give you the following fun fact, which is 2003, the share of zero carbon energy in California was higher than it is now.
Exactly.
Okay, and we've spent millions of dollars, billions of dollars for renewable energy, and we're behind the curve. But it's because of Diablo Canyon. So no, I mean, I completely agree with you. I mean, but nuclear is certainly not well liked in California. So even though it is the solution.
Okay, sir in the middle here, and then over there.
Maybe I misunderstood something, but so your objective is to minimize the standard deviation of the hourly output.
Yeah, well, that's certainly. I'm just saying I want to be on that efficient frontier. I either want to be on the highest capacity factor or the lowest standard deviation of that capacity factor.
Your system naturally needs some standard deviation because the standard is not the same by night and by day. So
no, this is done this was done on an annual hourly basis. So what I'm doing is I'm computing the hourly mean and variance. And then what I did here is in this graph is I did it by hour of the day. Okay, so think of it as each one of those things is hour of the day, but the problem is you can't build and destroy units each hour of the day. You build them and they last for the entire year. That's why I think you can measure intermittency at various horizons, but I've also done it looking at, say, daily output and looked at it, but the same sorts of efficient frontiers look very similar. If you're looking at daily output, if you're looking at weekly output, they look very similar. But the idea is just simply to say, is I'm building an amount of capacity. The question is, where do I want to put it? And I want to put it at the locations that's going to give me the most output for the given amount of volatility and output that I get. And what it's saying is right now, we're not doing a great job, and the logic is pretty simple. It's because that's not what the incentive that investors face, and so they're going to invest in the locations where it makes most money. And the evidence we showed is that, yeah, the revenue, you're closer to the revenue frontier, consistent with that logic. You're farther from the output frontier. How do we try to internalize that? Because that's essentially a bit of a free lunch. If we can get people to internalize that, then for the same amount of spending, we can get more renewable output on average.
So your standard deviation is for monthly or weekly?
It's, in this case, it's hourly.
I think I'm going to have to shut us down because we're out of time. And then you can ask Frank quick questions at the end, one-on-one. So thanks again.
Sure.